no, you cannot write, you cannot find a function so that its derivative is going to be equal to the friction force, even if it is static friction. That's not, that would not be the case. Because it can vary.
Seems like if you have a system, you put an external force on it and nothing happens, it's got to be storing that energy.
Yes.
It's not moving, though.
It's also that friction is a force at a given spot, because the goal would be to find, you see, a function u, so that your friction force, for instance, its x component would be given by minus du dx, and so on for y on z. And well, I could imagine a setup maybe where you could find a function like that, but the problem is also that friction is defined only at the point of contact. So you cannot really define a function everywhere in space to be able to do that. So I've never seen a problem where you can turn friction into potential energy. But you're right that if you apply a force at the microscopic level, what is happening is the molecules get bunched up together. And you could imagine it's plenty of springs that are storing the energy. But sometimes also what is happening, you have deformation. And it can go into also the vibrations of the molecules. And then you have some energy that turns into heat. So I think even on the theoretical level, you cannot say that friction derives from the potential function because of all of that. And you can see that there are problems with this. Okay, so that was what to say with this problem. And you see, you can do some cute stuff with Mathematica. You can play with manipulate. Okay, so let's continue our work through chapter 13. So let's look now at another set of coordinates. What do you think we are going to look at? We've seen rectangular, what did you say?
Oh, polar.
Polar, yeah. So we have to look at polar coordinates. And it's, again, F equal ma, but you write your system of equations in a polar system of axes. So you have on R axis, on the theta axis. Let's do that. I took the wrong folder. Let me just give you the summary and then I'll grab my notes from my office. So it's more a reminder of what we did in the previous chapter. So recall how it works. You have your R coordinate, and you have also a theta coordinate. So this defines a u r hat and a u theta hat. Of course, we're going to write F net is equal to ma in a set of axes r and theta. So the question is, what are the values of a r and a theta? So it's a reminder of what we did in the previous chapter. And actually, you had to use these formulas in your in exam 1. So what was it?
R double dot minus R dot B dot squared.
Right, there's no R dot.
Oh, right.
So that. And the other one is 2 R dot theta dot plus R theta double dot. When you get used to them, you can think through them and find them again. And there is, of course, if you have a third coordinate, it's going to be the z-axis, and you would get AZ is equal to z double dot, just like in rectangular coordinates. So then you apply F net is equal to MA. So you're going to have a radial component of F and a transverse component for F. So it's going to be FR and F theta. And you might get on FZ. So then you can say FR is equal to M times AR, and F theta is equal to M times A theta. So let me grab my folder. It's the same color. That's why I made this mistake.
In this case, you have to use Pythagorean's theorem to get F net from FR and F theta.
If you were to look for it, yes. But not necessarily. You would use the Pythagorean theorem for any system of axes because the axes are always perpendicular. And this way, Evan, I can give you back your exam. So let's do, I have 91, that's a good one. Here is 91. It's on page 141. You see you have a rod that is pushing a ball that is on a track. I'm going to draw it if you don't have the book. You were given a book or not?
I had the other book, but the problems are almost never the same. So
would you like a book?
Do we have extras?
Yeah.
All right, I'll get it later.
Okay. We do.
It's fine. I usually just wait for them to draw it on the board.
All right.
Okay, so I better do a good job drawing it. Oh, yeah, it's not too bad. So you have a rod that can rotate about some point O here. And it is pushing a ball that is confined to a track here.